fundamental counting principle. So in this chapter, what we're going to look at is we're going to solve problems that you can use the fundamental counting principle, permutations, and combinations. A lot of the questions you can actually do using the fundamental counting principle, so we'll keep coming back to that as we go through this section. We're going to explore patterns in the expanded form of x plus y to the power of n. So things like 2x plus 3 to the power of 7. Can we expand it out without having to do the distributive property 7 times? Because that would be very time consuming. So we look at our introduction. Joe is shopping for a car. So the dealer has 3 different models, and each model is available in 5 different color choices. So if we made a tree diagram, we could see how many different choices that Joe would have. So you can have Model 1, Model 2, Model 3. Each model comes in the 5 colors, so his choice could be Model 1 in blue, or in red, or in purple, or in white, or in black, Model 2, etc., etc. So how many choices does he have for cars? 15 choices. How many models does he have to choose from?
3.
How many colors?
5.
How could I use 3 and 5 to get to 15?
3 multiplied by 3.
That basically is the fundamental counting principle. It says if you have a task that's made up of several stages, and if you have A choices for the first stage, B choices for the second, C for the third, etc., the total number of ways that the task could be completed would be A times B times C times however many tasks that you have. So if we look at the first example, we have this wooden toy. The toy comes in 3 parts. The top part can be red, white, blue, or pink. The middle can be orange, purple, or black. And the bottom can be yellow or green. So if we were to make a tree diagram, what it would look like is we have the first part. So what are my choices for the top part?
Red, white, blue, pink.
Red, white, blue, or pink. And you're going to want to leave some space between each of these colors because my tree has to fan out. So then I have the second part. How many choices do I have for the middle? Or what are my choices for the middle, sorry?
Orange, purple, and black.
So I can have a red top, and then an orange middle, or a purple middle, or a black middle. And that will fan out from each of these colors, this orange, purple, and black. Orange, purple, black. And then again, orange, purple, and black. And then I have the bottom part, or part 3. And what are my choices for part 3?
Yellow or green.
Yellow or green. So I have yellow and green that come off of each of these. So notice how it really starts to get squished after a while. Getting really squished. So then my toys could be that I have a red, orange, yellow toy, or it could be a red, orange, green toy, or red, purple, yellow, etc. All the way down to the last one, which would be pink, black, and green. So how many toys would I have in this list? $24. Because this would be 1, 2, 3, 4. If I count the yellow and greens that I have branching off, each of those would lead back to the beginning. So if I use the fundamental counting principle instead, the first part has 4 choices. The second part had
3.
And the bottom?
2.
And what is 4 times 3 times 2? Much faster. So in the previous example, the toy consisted of a part 1 and a part 2 and a part 3. The word "and" gives you that multiplying factor. So when we see the word "and," we know that the total number of arrangements is going to be found by multiplying. In class example number 2, we have a Math 30 quiz. There's 8 multiple choice questions. Each question has 4 possible choices, A, B, C, or D. How many different sets of answers are possible? So how many choices do you have for the first question? 4. How many for the second?
4.
And the third? 4th?
4.
5th? 6th?
4.
7th?
4.
And the 8th. What operation goes between all of these? Think of this as being task A, and then task B, and then task C. So the word "and" would be multiplying. If I take 4 and I multiply it by itself 8 times, can I simplify that? Four to the power of 8. Which would be how many possible sets? So 65,536 different possible sets of answers that you could have. And that would include things like all 8 questions are answered by 8, which screws people up because that would just make you double check and question everything. Okay. Not every question is quite that straightforward. Sometimes we have restrictions. If we have a restriction, deal with the restriction first. So for example, Eric's assigned the task to determine how many odd 4-digit numbers there are. He's been told that a number such as 5,267 is a 4-digit number, whereas 267 is not. Putting a 0 at the front does not allow it to be a 4-digit number. The first step of his work is shown. Explain his reasoning for having the number 5 in the last spot. What does the last number correspond to? It's the choices for the last spot. In order for it to be an odd number, it has to end in a 1, 5, 3, 7, or 9. So the last digit must be odd. In his second step, Eric puts a 9 in the first spot. Why is there a 9? What are his choices for this first spot? It can be the numbers 1 to 9. What digit can't he use in the first spot? 0. That's the restriction. So it says complete his work to determine how many odd 4-digit numbers there are. So we have the 4-digit numbers. We know that in order for it to be odd, the last one has to be 5. And in order for it to be a 4-digit number, the first one has to be from 1 through 9. What choices do I have for the second spot? What digits can I put in the second spot? 0 to 9. So how many choices do I have? 10. And what about the third spot? 0 to 9 again. So how many choices? 10 again. So I would be multiplying these together. And what is the product of 9 times 10 times 10 times 5?
4,000.
So that's the number of odd digit numbers, 4-digit numbers that you could come up with.
Why did he know to start with the 5 at the end? Like how? Why not one of like 1 or 3?
You could start in either spot. It's just if there are restrictions on your 4-digit numbers, start with the restrictions. It just makes it so that you're dealing with that first and getting it out of the way. Because if you had no restrictions, if this counted as a 4-digit number, then I would have 10, 10, 10, 10 choices. But that's not what I have in this case. First of all, I have that it has to be odd.
Oh, okay.
So I deal with the oddness. And then 0 can't happen here, so I deal with the fact that this can't be a 0.
Oh, okay.
That's what it means by the restrictions. Deal with the stuff that you can't have. In the second part, Eric's now determining how many different odd numbers in which there are no repeating digits. So he can't have 3, 3, 3, 3. He's only allowed to use the 3 once. So if I look at his first step, why is it still valid to start with this first step? To say that there's still 5 choices here. Still looking for an odd number. So I still have the choices of 1, 3, 5, 7, or 9. But how come the second step is not?
I had 5. So you only have 8 possible choices.
Yeah. Don't confuse this 5 with this 5. But your reasoning is still the same. I'd have 8 possible choices in the first step because I can't have the last. So if I use a 3 here, I can't use a 3 here. So that only leaves me with 8 choices because I can't have the 3 and I can't have the 0. So I can't have the last digit and I can't have the 0. So now if we can finish it off, we know that there was 5 here, there was 8 here. How many choices do I have for the second spot?
Maybe 8.
Why 8?
Because you can't have the first, you can't have the last.
Right. So I can still use the 0 through 9 digits, but not the first or last, which is what gives me the 8, 10 minus the 2. How many do I have for the third spot?
You have 7,
Why 7?
because you can't use the first or the second or the last.
Exactly. So how many possible odd digit numbers do I have now? So those would be the number of odd digit numbers that would have no repeating digits. Imagine doing a tree diagram for this. Exactly. The look on your face was like, okay. Car number plates in African country consists of a letter other than I or O, followed by 3 digits, the first of which cannot be 0, followed by any 2 letters which are not repeated. How many different car plates can be produced? So, we read it again. Car plates consist of a letter, followed by 3 digits, followed by 2 letters. So what do I know about the first letter?
It can consist of any letter except for I or O.
Okay, so how many letters is that to choose from? 24. Okay? Then I have my first number. Is there any restriction on my first number?
Cannot be 0.
Okay, so how many choices do I have?
Wait, no. Oh, wait. Yeah.
9 choices, 1 through 9.
I have no idea.
Is that
Okay.
just assuming?
Oh.
Because that's assuming that it'd just be like a single digit.
Yes.
Okay.
Yeah, they're single digits. So then what about the next 2 numbers? Does it say whether or not the numbers can be repeated? It doesn't say that they can't. It just says the first one can't be a 0.
So 10.
So 10 and 10. Okay? And then followed by any 2 letters. So how many choices do I have for the first spot?
23.
Not 23, any. So it could,
couldn't be repeated.
Yeah. It says
these 2 letters can't be repeated.
Oh. So it'd be
So-
24 and then 23.
Not 24, 26. Because I can have the I and the O now. I can't start it off with an I or an O, but I can finish it off. And then the next one would be 25, because that's where I can't have the repetition. And it could be that I's and O's are specifically reserved for governmental plates. And that could be why. That could be the only reason why the I's and the O's are not allowed. So how many car plates could be produced? Who wants to read the number?
14,040,000.
Good.
Getting there.
I know calculators don't put it into threes for us very nicely. So if you think of an Albertan license plate, which is 3 letters followed by 3 numbers, how many different plates that can produce? That then leads into the question why some of the new license plates have 4 letters. Because now you're adding in a whole new set that can give you a lot more. It also brings in the idea of why area codes were added into phone numbers and all of that. Because when I was growing up, if I had to dial somebody else's phone number in Fairview, all I had to do was 5 and then the next 4 digits. So if I was phoning the school, it was 52245. And then it changed, so all of a sudden you had to use the 835. And then we added in the area codes, the 780, and that was added in because we were running out of phone numbers. So the 780 allows that prefix of 835 to be used in northern Alberta with the 780, but then also with the 403. And now we have the, is it 251? What's the other? Yeah. So there's a 251 area code that's used all over Alberta. And the same thing, now you can have a 251 835. So adding those prefixes allows you a whole other set of phone numbers to be used.
250 is BC. 251.
I hear 251 at BC sometimes. Otherwise, just like I'm not out of the country or
The 251s are not very popular, but when they put in the 780, they split the province. So they said, I think it was everything basically south of Red Deer stayed as 403, because that used to be our postal code, and then everything north of that became 780.
That's why.
I just realized that.
So then when you were phoning somebody, or when you got a phone call and it came in as 403, you knew why, or you knew whereabouts they were from. Like, Craig was selling his motorbike, and we had listed it in Auto Trader, and Craig got this phone call, and the guy was talking about coming to see his bike. And so Craig's like, so where are you from? Because he could see on the phone that it said 403, so we knew. And he was talking about coming to see it like that evening. And they thought that Fairview meant there's a subdivision in Calgary that is a Fairview subdivision. And so he thought we were in Calgary, and I'm like, you didn't pay attention to the fact that you had to, like. So if we're determining an even digit, where does my first restriction happen?
The last digit has to be 2, 4, 6, 8.
2, 4, 6, 2, 4.
Is that it?
0.
Or 0? So how many choices do I have for the first?
We have 5.
I have 5 choices. Okay? What about my first digit? Can't be a 0. Why can't it be a 0?
Because then it's not a 4-digit number.
Exactly. So it can be a 1 through 9. So how many choices do I have? 9. What about the second digit? Does it have any restrictions? Or can it be anything?
0 to 9.
0 to 9. So how many choices do I have?
It doesn't say anything about repeat.
No, not in part 1. Part 2 has no repeats.
So 10 choices.
10. Okay, so 9 times 10 times 10 times 5?
45.
So this is the same number of odd digit numbers that Eric came up with. Now, Eric started his work to part 2, as shown below. He put in his 5, because it has to be a 0, 2, 4, 6, or 8, but then kind of got stuck. He didn't know where to go after this part, because he needs to consider 2 separate cases. With the repeats, the cases that he has to consider who can tell me? What are the 2 possibilities that he can have? So for example, what happens if he picks a 2? He has 5 choices there. What happens in the first spot? How many choices does he have in the first spot now? Only 8. Why?
Because you can't have the 2 again.
He can't have the 2 again, and he can't have the 0. Okay? But what happens if he picked the 0 here?
Well, then you can still have 9 choices.
Then he can have 9 choices. There are my 2 circumstances. So this is just not the 0. This is no 0 and the last as well. Okay, so in here, there's my even numbers. So we suppose that he picked a 2 here, and then he picks a different digit here. How many choices does he have here? So he's got the digits from 0 through 9. Let's say he picked a 2 here, and let's say he picked a 4 here. How many choices does he now have? 8. And then how many does he have here? 7. Okay? So 8 times 8 times 7 times 5? What do I get?
2,200.
Okay? So in the second possibility, we have that he picked a 0 here, which then gives him 9 choices here because he's got the digits 1 through 9. How many choices does he have here? So he took out the 0, he took out another digit, so 8, and then 7. Okay, so how many is that?
$2,520.
So all together, I get 4,760 possibilities. Is that more or less than what the odd numbers were? Significantly more. It's this many more. That 0 added a whole new set of numbers, having the just ending in a 0. Most commonly, a lot of the questions that you see that have to do with the fundamental counting principle are letter type questions such as this one. Consider the number of distinguishable 4-letter arrangements that can be formed from the word English. Okay? It says there is an implication that each of the letters in the word English occurs only once and cannot be repeated. So imagine Scrabble tiles. You have the Scrabble tiles with the letters for English, and you put them in a bag. And then you can pull them out. All we're looking for is 4-letter arrangements, not words. It's just what 4 letters could you have. It doesn't necessarily have to form a word. Okay? So it says determine the distinguishable 4-letter arrangements that can be formed if any letter can be used in any position. So if any letter can be used, how many possible choices do I have in the first spot? 7. So I dig around, I pull the first letter out. How many do I have in the second? Then? Okay, so how many is that?
840.
Okay. B. First letter has to be an E. The first letter has to be an E. How many choices do I have? 1. How many choices do I have for the second one?
6.
Then? Then? How many letters, or how many possible combinations?
120.
Okay?
Nice job.
Okay, the first and the last have to be vowels. What are our vowels? E and I. So I have 2 for the first one. How many do I have for the last one? 1, because I took one of them out. many do I have for the second position? Why 5? Because I took 2 of them out already. And then 4. Okay, so 2 times 5 times 4 times 1.
40.
Yep. Okay. And the last one is that the word has to contain the letter G. So, where could the G go?
Anywhere you desire.
Anywhere I desire. So let's put it right here. So then how many choices do I have for the second spot?
6.
Then,
4.
or I could put the G in the second spot. In which case, how many choices do I have for the first spot?
6.
Then 1, then,
5.
or the G could be in the third spot, or it could be in the fourth spot. So really it's taking this 6 times 4 times, 1, and multiplying it by 4 to account for this G moving in 4 different places. So what would that give me? There you go. Okay. So 4, 5, and 9.
12 times 4 is 40.
10, 14, 16, 17, and 18.